Thank you, guys. Thank you so much. Okay, well, yeah, really, really nice to see so many faces, especially coming out of a grueling session for the entire day. And am I audible? It's everything okay? Okay, great. Sounds good. So, the idea is to kind of, get into the natural language domain, see what do we have there, and learn some technology in terms of, how the domain has changed over a period of time. And basically, about a decade ago, when I just graduated out of PhD, I was working for this one guy, about 70 years old. He asked me one thing, Nish, what do you think is the half-life of your PhD knowledge? And I'm like, what does that mean? He's, the knowledge which you created has a half-life and it's going to dissipate. Like, no, mine won't. But as arrogant as I was, 10 years later, I realized that most of the core technology which I had worked about a decade ago has had a paradigm shifting effect in the whole domain. And this, natural language as a domain has changed significantly in last 10 years or so. And so what we will do is we'll touch on the technology. We will touch on tools which have enabled the technology to go as fast as it did. And then, I'll provide you some of my professional tips. So, we will start with what is natural language understanding. We'll look at the old classical model versus the new vectorized models, and then touch on the NL tools, the word-to-vec models, which are more newer generation deep models, and then the granddaddy of natural language tools, which is essentially NLTK, Natural Language Toolkit. We will also then touch on the generic deep learning tools and how do we use them in natural language. And finally, what I'll do is I'll take up a use case, which is intent classification, and then walk you through that use case. And as you understand more and more, you will probably be able to make it work for your own problem. Sounds good? So let's start. So what is natural language understanding? There are multiple use cases of natural language understanding. Information extraction. Hey Siri, can you schedule a meeting for me at 10 a.m. tomorrow at my office? And so Siri understands that you are talking about scheduling, you're talking about a meeting to be scheduled at a certain time at a certain place. And so it is basically able to extract structured information from unstructured text. Sentiment analysis, very prevalent, typically a lot of toy use cases come up, especially I have analyzed Twitter sentiment, and what, people are very negative about one company. That is another use case. Context summarization or contextual summarization is another use case. So typically, we have heard, how can we summarize an entire web page into a paragraph and stuff like that. Contextual summarization is I extract a particular context out of the entire paradigm, and it can essentially be, say for example, I have a legal document, and legal is actually a very good example here, because typically legal guys would not get into fight by themselves. There has to be an instigator. Either it's legal because of medical injury, legal because of domestic events, legal because of Kaveri river water and stuff like that. So there has to be something which drives the legal guys, hey, let's go and get them. So that is the context. So what do you want to summarize? Do you want to summarize the medical part of it, or do you want to summarize the legal part of it? And at that point comes the fact that you create the context and then you summarize that context. Classification is one example we will look into, and it is essentially classification of intent, classification of documents, or multiple different things. Machine translation, Google did a fantastic job, basically killed the game for everybody now. It used to be a huge area of research time ago, but now they are so good at it, nobody really wants to get into it because it's a solved problem. Topic modeling, identify topics or trends, things like that. So, there are some companies out there, what they do is they take a news article, for example, and say, 3 days later, would this news be still relevant? And if it will be, how relevant it will be. Company apps like Quora, for example, would love to have something like that. Hey, a new question came in. What is the half-life of this question, right? So they want to know what is the trend. And then entity extraction, again, a problem which has been around for a while. Identify nouns, person, place, animal, thing, or companies, organizations, and all sorts of those things. So that is essentially a broad picture of what natural language is, what it can do for you. How does it do it? Let's just take a quick example, and this is a classical model I'm talking about. The old version of how a natural language model used to be built. So if you have an example like the cat sat on the mat, you have a sentence like a cat sat on the mat, typically we will approach it in two ways. One is we will create tokenized features out of it. So cat would become one token, sat would become another token, mat would become another token, and you have that. Then, this is called bag of words. Now, somebody says, hey, but, you haven't created captured the context in terms of the cat actually sat on the mat, right? So then you start saying, okay, I'll take bigrams. I'll take the combination of the and cat being one token, cat and sat being another token, and so on and so forth. And then eventually trigrams, and at some point of time you get into diminishing returns, so quadruple and something like that, and then you basically stop. The other set of features which we can create are linguistic features. Typically language has had a huge impact on how we speak, how we structure sentence. So why don't we use language as a way to create features, right? And so that is where you will start saying, hey, you know what? Meanwhile, I actually have the cat as a noun over here, and so why don't I put another feature associated with cat, and that helps me create new features, right? And so that is really, a whole set of feature engineering which comes, that is where the whole set of feature engineering comes into picture. So lexical analysis for that matter, for example, and so that is basically identifying, analyzing word structure. So I have the word sat, for example, right? So I can have sat, sitting, sit, and all sorts of those things, and I root it down or lemmatize it down to to SAT, and then what I do is I increase my word transition probabilities, and so I don't need as many feature vectors, right? So that is lexical analysis. Syntactic analysis is very simple. It is basically capturing the syntax of the sentence. So the was the first letter of the sentence, and Matt was the last letter of the sentence, and there was a comma, an exclamation mark or something that is captured. Semantic analysis is extracting the meaning on context, and in the same thing. Disclosure is extracting meaning from conversation. So what basically, when you are writing something, you change paragraphs, right? But so you have a context which carries on from one paragraph to another, and that is essentially this. What you are doing is you are carrying over the semantic meaning of the semantic meaning across. And as we are having conversation, then that is called disclosure. Pragmatic analysis has been a real stone for researchers because now what you have to do is you have to identify interpretation. And how do you identify interpretation when you have maybe sarcasm in place, that becomes much more difficult, right? So this has been a problem, and basically what happens is between bag of words, n-grams, and multiple multiple linguistic features, if you have a decent enough vocabulary, you are looking at creating maybe 18,000, 20,000. That is something which I have typically worked on. Features of about 18,000, 20,000 feature set. And that creates a problem, right? So now what we are going to do is just quickly look at, how does creating these many features affect our machine learning algorithm. So, the biggest problem is what is called the curse of dimensionality, right? What it really means is you had, say, for example, 10 features in one dimension, and you were able to capture or have representative training examples of all those 10 features in your training set. However, the moment you put in another dimension, then you have to look into creating 100 representative sample, and then third dimension you want 1,000 training samples, and at some point of time you run out of representative examples which explains the relevant variations, right? And so then what happens is your training data becomes sparse, and at that point, God knows what will happen during the test time, right? So that is one bigger problem here. The other thing is that as we just did, what we did was we manually created feature vector from the data, right? Who knows? Maybe we missed out something, right? Who knows? Or we could have, we oversimplified or we undersimplified. But that is what we knew, so that is the best we did. So handcrafting feature engineering, well, it was good while it lasted, but maybe we should think more, right? And then the other problem is the same operator gets applied repetitively again and again. And so, in just the previous slide, we saw the word cat, and the and cat was the noun phrase, and sat on the mat was the verb phrase. So essentially, in the feature space, what you have is you have one single token applied to lots of features, right? And because the resolution of the top feature was much higher or much broader, and the features in the lower side were much finer, right? And so, by the way, I had actually done some work here, and I have actually published a patent on how you can use this. Basically have features of different resolution around and still make your machine learning algorithm work good. But that's a separate this thing. However, that still remains a problem in the system. And then the other problem is speech data or text data is all around. It gets created very, very significantly. And so, but to label this data is very expensive. Somebody has to actually read it or listen to it and then label it, understand the meaning and all sorts of those things. So data labeling is a huge issue in natural language domain. So then we shift into the newer generation of system, which is as you heard, it's relatively new, and what it does is we create vectorization models, and what vectorization model does is it basically learns a relationship between words from a very large corpus. So essentially, what the way I would put this problem is, I have the word sat, and if I take the word sat out of this sentence, and I'm looking at two words to the left and two words to the right. So I'm given the sentence the and cat, or the words the and cat, and on and the, then basically what I have to do is I have to predict what would the most likely word be in the middle. So that is really what I'm predicting. I'm predicting the probability of the word sat sitting over here, given that two words to the left is the and cat, and two words to the right is on and the. And so you keep on doing that for the whole thing, and then you create basically start creating the word vectors. And so basically, what you're trying to do is you're trying to find a similar word given the neighbors, and to get into it, it uses some similarity measure, which typically is cosine similarity. And the way it will work is, you created this, and then what we have is these would be the neural net layers, and what these layers would essentially do is you can have them looking at different resolutions. So it captures the context, it captures the semantic and the syntactic meanings, and the fact is that you need a very large corpus over here. But if you have large enough corpus and you let different embeddings have different resolution, then you are hopefully capturing a lot of different variants in the data, and that would then be the convoluted. Convolution is basically autocorrelation. So you have something like this, and when the two things are similar, you have a spike, and so on and so forth. And then when we convolve it, at that point we can also do some kind of summation kind of thing, which is essentially is max pooling layer. And at this point, you can basically stop if you want an unsupervised algorithm. But if you want a supervised algorithm as a classification or something, what you do is you put a spline or a softmax function or a tanh function, and basically say anything on the bottom is one class, anything on the top is another class, and so you have basically being able to create a classifier from the sentence, right? So, that was good, this thing from what the classical model was, what the vector model was. Let's look at, some of the tools which has enabled us to achieve what we achieve right now. So, so basically, word2vec is a word vectorization tool which was created by Thomas Mikolov when he was in Google, and it was well, the thing is, Google had it in around 2006 timeframe. They released it publicly in 2011 timeframe, and basically what it does is exactly what we saw in previous slide. It's an algorithm which basically creates layers, and word2vec in itself is not deep, but you can make it deep. So the more the embeddings you have, the deeper it will become. The cost impact is you have to have bigger corpus and stuff like that. The thing about word2vec was when it came out, it was pretty hazy in terms of how the math would work and stuff like that. So 3 researchers from Stanford, Jeffrey Pennington, Richard Saucher, and Christopher Manning, they looked at it and they created something called as GLOVE. GLOVE is an acronym for global vectors, and what GLOVE does is it kind of demystifies word2vec, and it creates the factorization matrix, and they also provide a lot of intuition in terms of how this works. And so after that demystification, what happened was, Gensim came along, and these guys were already there, and their motto was essentially to write open source software which creates similarity. So given one document, can I find all the similar documents to that? And when word2vec came along, and after GLOVE, they were able to create such similarity, and they implemented the word2vec when it kicked off for DIY researchers, do it yourself. I don't have a I have a CPU, not a GPU, but can I do deep learning? And so that is where DIY researchers came along and started becoming more involved in such this thing. Otherwise, before that, it was essentially for enterprise. And 2 tools, Stanford NLP and NLTK, and Natural Language Toolkit, have been around for a very long time. A lot of people have got their masters and PhDs working on these toolkits, and this is, as I said earlier, this is the granddaddy of toolkits. And essentially, what will happen, what used to happen was, they would be funded by government agencies like DARPA or science agencies and stuff like that. And what they would do is handcraft features. So take 5 years worth of, say, Wall Street Journal, and go line by line and create feature vector for all of them. And that is why these tools are still, they are still, I wouldn't say it's irrelevant, but it still exists and are used. And some piece of these tools are, for example, tokenizers and all sorts of different things are still very, very relevant even in this domain. So those were the specific to natural language tools. Now you look at more generic deep learning tools, and one of the deep learning libraries which came out of academia is Theano. Theano basically focuses on automatic differentiation, which is very important because it helps you create, run back propagation algorithm for every time you change something in the neural net. So, it automates that significantly. Somebody was talking earlier. They said, yeah, we do all sorts of these fancy things, but do we really understand the math? The thing is, some people understand. Some may not want to understand, but they still want to use it, and that is really what Theano helps you do, even if you don't get it in terms of the raw math, but you can still use it, which is, why not? We don't really understand how a V12 engine works, but we still drive a car, right? So it's exactly the same thing. Right, and then a lot of these guys who initially started at Theano then, got a job, and they got job at Google, and so they came to Google, and then they built TensorFlow. TensorFlow is better because it comes from enterprise domain in the sense that, it runs faster than Theano. It runs more algorithms, reinforcement learning and all sorts of those things. Supports Python with C++ background, though it kind of leaves out the Java and the Scala community, but that's okay, maybe it'll come along. Those are good. And Keras is really the car I was talking about. So if you do not want to get into anything, and if you still want to use deep learning algorithm, then here comes a Python library with very fancy APIs, which in the background can run either Theano or TensorFlow, and get you what you want, get you to your destination. And so, if you don't want to get into one of these big guys, you can sit in Keras and still have a joyride in the deep learning domain. Why not? So those are the tools. Let's quickly look into the tools, and I'll just do a quick time check. Okay, tips. And basically, what we have is, as I was earlier saying, a lot of people work with the sentiment analysis as a use case. And it's a good toy example, but I really feel like they kind of, without understanding the domain too much, they kind of get and start fitting the positive, negative, neutral sentiment to the problem. And what if I say, really the sentiment was not positive, negative, or neutral, but it was happy, sad, mad, and glad, right? Or this picture comes from my doctoral dissertation, which basically says, the emotion can also be categorized as the way people are talking. So when I say a newsreader, which I call reportorial prosody, what it really means is a newsreader is trying to give you facts and facts only. They are not trying to give you interpretation. You are supposed to make your own interpretation. It may not happen in real life, but that's how it should be. That can be repertorial, there can be human interest, there can be, poetry, theater, all kind of prosodies. And I can start looking at emotions in that direction. Not everything, there is still some half-life left to the dissertation, by the way. So let's quickly look at the intent classification, as a use case. And what is, I provide an example of the data over here. It's a JSON structure. Just I'll quickly go through how the structure is. There is a, the entire thing is embedded inside date, and then within date you can have multiple such conversations which can happen. One such conversation has an ID 1, 2, 3, 4, 5, by name Brian, has certain date of birth, is a registered user, and Brian comes in on a platform and quickly, how much time do I have? 5 minutes, okay. So Brian comes on and quickly says that, I don't know my PIN number, can you assist me? Now, the good thing is, the person in the background is essentially there who just listens to it and runs an API, creates a PIN number for you, right? If I could identify this intent, I would be able to immediately run the API in the background automatically and be able to self-serve this customer and would not need an agent, right? So, how would a typical model, such a model would look like? I can create one model for unstructured data. I create a model for unstructured data. I bring the two models together to make a final prediction. I can get into the details, but we will skip that for now. And then, what I can do is, the word vector representation, which you just saw, I can take that vector and I can collapse it into two-dimension domain using a nonlinear collapser, something like tsne or something library, and then start looking at how discriminative each feature is to that class. So, for example, if I look at something over here, maybe the guys in the background would not. So I'll pick this credit limit and credit limit increase. Two classes which are very close to each other. That basically means the underlying feature vector was not able to discriminate these two classes together. I may need more data, I may need newer features, something like that. Our account PIN feature sits over here, fairly separable, and so I can say, okay, I have enough discriminative feature for that intent. So I will quickly, look at the other problem can be how do I fine tune this data and stuff like that. We can actually skip this if in the interest of time, and as well as so a shameless self this thing. I have a workshop tomorrow where we can go over the theory and code for this example which I just showed you, and that workshop is practical natural language understanding, from data to intent. So we will start from data and land at the intent. My colleague John Kiran would be there